Hello, everyone. So you might know me now. I'm Raja. I'm responsible for the communication of the Quantum Energy Initiative. And this is not so random because I'm actually working on quantum communication. So I'm going to present you this work with these beautiful people called Energetic Analysis of Emerging Quantum Communication Protocols. And it comes from the same idea of the QEI as a whole. We live in a world with finite resource, and it's important to define figures of merit and benchmark to emerging quantum technologies. And this work that I'm presenting to you is the first estimation of the energy consumption of quantum networks. Excuse me. So our quantum communication in general. All right. And yeah, it's a bit different than in the computing platform where the qubit has kind of a big energy because it's embedded in cryogenics or it has control electronics on it. Here, the carrier of information is the photon, which in itself has little energy, and in the fiber, there's no energy. So the important parts are the source and the detector, the preparation of the photon and the detection of the photon. And now I will answer some questions such as, how much energy do we need to run standard communication protocols? What are the trade-offs between protocols achieving same functionality? What are critical components in a quantum network? And the ultimate goal of whatever we're trying to do is to find energetic advantages of using quantum networks over classical networks. I'm not doing that now, but this is the ultimate goal. So let me start by a small teaser. What if I told you that generating 1 gigabyte of secret key with BB84 is equivalent to running 100 washing machines? Yeah, you just run them like a standard cycle. You know, I don't know, it's like an hour and a half, 2 hours, I don't know. I mean, of course, I have to say there are a lot of asterisks. So with generating 1 gigabit of secret key, I mean, at 25 kilometer with recurrent state at 1550 nanometer with cryo-based detectors and from start to finish, including the cooldown of the detectors. So I will come to the details later. Also, this is obviously a back of the envelope calculation. 100 washing machine, it's like, yeah, it depends on the washing machine you have, and it's without counting the water. So yeah, let me get a bit more precise, and let me tell you the method. So the idea is simple. We just sum the energy consumption of all the hardware that is involved. So it's very hardware dependent, this method. And so this is this formula that looks maybe ugly, but it's very simple. It's just the source, the manipulation, so the wave plates, the motorized wave plates, and modulators and stuff like that. The detection station, the classical cost that corresponds to post-processing and also the sometimes coin flipping or other protocol that happen during the protocol, and the initialization cost, so the cooldown of the detectors, for example, of each of these elements. And so thanks to this formula, I can have the energy consumption of a protocol for a certain time. And what I will do is compare the energy consumption of some standard bipartite and multipartite protocols that achieve the same task. So I had wished to compare this with a classical equivalent, but for most protocols that I'm looking at, there is no classical equivalent. So this amounts to what Olivier was saying yesterday, is to find if the energy cost is acceptable or not, more than looking at if it's better or not than classical. So for bipartite protocols, I will look at QKD, quantum key distribution, where the goal is that Alice and Bob generate a secret key. There are many protocols achieving the same. Here are 3 so-called discrete variable protocols. Discrete variable means that we use single photons. So you have BB84 where Alice sends a photon to Bob. I mean, I'm not going into the detail, but the main point is that the hardware is different depending on the protocol, and they also achieve different rates. And on top of DV QKD protocol, I'm looking at CV QKD protocol, continuous variable, in which the information is encoded in the quadrature of the electromagnetic field of wave packets. Again, not going into detail, but these are 5 protocols achieving the same task, and that allows me to see, okay, which one is the best, which one is the worst. I look at 2 figures of merits. The first one is the so-called energy efficiency that comes from classical papers that I've read on the topic. And it has this simple formula. So it's how much power do I need to input in my system to achieve a secret key, a certain rate. And the interesting thing about this setup is that it's not like if I input more power, I get more rate. The rate is set by the setup, the distance, the hardware efficiencies, and it doesn't help to input more power. And the second figure of merit that I'm looking at is the cost. So this one is more concrete. How much does it cost to generate 1 gigabyte of secret key or any target of secret key? But here I will show 1 gigabyte. So let's dive in. Let's see how GV-QKD protocol are comparing and using these two figures of merit. So the first figure of merit, as I said, is the energy efficiency. You can see here the energy efficiency of BB84, entanglement-based QKD, and measurement device-independent QKD. And you can see that, well, BB84 is more efficient than entanglement-based QKD, that is more efficient than MDI QKD. This tells you something, but on the other hand, it's a bit trivial because BB84 has the higher rate. It has a very high rate right now, while entanglement-based QKD has a rate between the two, and MDI QKD has a very low rate. So this tells you that the faster you can perform a protocol, the lower the energy cost is. So it's a time-agnostic quantity. It doesn't take into account initialization. And it's interesting in the future, but also it's not very telling. Like if I tell you that the energy efficiency of BB84 is 1200, sorry, doesn't tell a lot. So this is why we started looking at a more concrete figure of merit, which is how much does it cost to generate 1 gigabit of secret key. This is relevant for what's happening now. So I turn on my setup, I generate my secret key, and then I turn it off. And then you will see some trade-off appearing. So first of all, you can see that BB84 remains the most energy efficient protocol. This is because it has the highest rate, and it also only involves one detector and one laser, so simple. But then you can start to see some trade-offs. MDI QKD has a very low rate, but it uses only one detector station in the middle, while entanglement-based QKD uses 2 detectors. And the detectors are cryogenic-based, and they are the ones that cost the more energy. So for short-ish distances, up to 70 kilometers, it's better to use measurement device-independent QKD, even if it takes longer, but it costs less energy from an energy point of view. So maybe this still seems a bit blurry, so I'm going to go a bit more into detail in how do I compute this, taking BB84. So in BB84, if I want to know the cost of BB84, I choose a setup. I ask my experimentalist friend to tell me what's in a BB84 setup that costs energy and to give me the power. And in the article, you will see a big list of hardware elements and with their power consumption, their initialization time. And I really thank the experimentalist around me for that. So in BB84, you have one laser, one modulator to attenuate the pulse, one detector, and you see that it has a big power, 2 computers, one for Alice and Bob, 2 motorized wave plates to choose bases and stuff like that, and 1 time tagger to time tag. Then you look at the initialization time of each of the components. There is also a bold choice here, which we chose to use 24-hour cooling time for these detectors, which I know can be done faster in Candela, I think, but this is what the time we had in the lab in Paris I was looking at. Then you estimate the time it takes to generate 1 gigabit of secret key with this setup. So we can go more into detail of that. I don't have time right now, but basically, for distances of order of 10 kilometers, it will take you 200 seconds. We can discuss more of that later. And then you just plug into the formula. So 200 seconds times the power of each hardware plus the initialization cost. And you see this huge number here, which is the initialization cost of this cryo-based detector, which is the dominant factor. And then you can conclude, okay, we need 259 megajoule to get 1 gigabit of secret key. And this takes 200 seconds plus these 24 hours necessary to cool down the detectors. So now, like we have a method, I can tell you the energy cost of producing 1 gigabit of secret key, and I can start playing with this hardware list. And the first thing that is obvious to do is to change this detector that costs so much. So this is what we did. So the cryo-based detector are called SNSPGs, and they are an alternative to them called APGs, which work at room temperature, but they have a much lower detection efficiency. So you have a trade-off, and you see here like the cost of producing 1 gigabit of secret key using this, like one of the 2 detectors. And you have a very striking result, which is that at 25 kilometers, using APGs takes three times longer, but consumes 60 times less. So to give you more concrete things, it takes half an hour to generate a secret key using APGs, while it takes 10 minutes with SNSPGs, but it consumes 60 times less. Again, like the gain is huge. So yeah, this depends. And then you can play more with the hardware. Instead of changing the detector, you can change the wavelength. If you work at different wavelengths, you use different lasers, different detectors. So we have the whole list. And the main problem when you change the wavelength is that the fiber that we use are optimal for telecom wavelength, which is 1550. And if you use another wavelength, then there is much more losses. So you are very limited in distances. But it appears that for short distance or very short distances, 5 kilometers, 300 meters, using infrared wavelength or visible wavelength result in a lower consumption than using telecom wavelength compared with the standard setup. So this means that within a building, it could be interesting to use a different wavelength to optimize the energy consumption. So you can imagine hybrid quantum network working at different wavelengths if you put the energy consumption as the main benchmark. So yeah, after dVQKG, we can look at CVQKG and see if it's better or not than dVQKG. And CVQKG, the main point is that you use so-called off-the-shelf telecom components, so the components that are used right now in telecommunication devices. And they are super optimized, so overall it uses much less energy. There are different schemes, I'm not entering into detail, different schemes to do CVQKG. There are homodyne detection, heterodyne detections. So we look at all of this, and you see that for distances below 100 kilometers, the energy consumption is of the order of a few megajoule. The QPSK scheme performs at low distances, but okay. So it seems that CVQKG wins. But in fact, it's not necessarily true if you start taking into account the post-processing cost. Because CVQKG has a much more complicated post-processing procedure. And here in orange, you can see it's the CVQKG cost. Here, without considering post-processing. And here, considering post-processing for different values of the post-processing. And in blue, you can see the dVQKG that I was showing before. And it appears that considering the cost of digital signals processing, CVQKG consumes more energy than dVQKG. So this stresses the need for efficient classical post-processing for quantum communication protocol, but I'm sure that in the future, that this is basically a classical optimization problem. This will be solved, I'm sure.
Software, hardware?
Software. This is a software issue. So yeah, that's it for bipartite protocols. Let's go now to more interesting things, which are multipartite protocols, because we want to talk network, not only Alice and Bob, right? So in a setup where you have n parties connected with fibers or with free space, the idea is to generate entanglement between everyone to perform protocols. Example of protocols are anonymous transmission, conference key agreement, electronic voting. There's like a whole zoo of protocol. And most of them are based on sharing multipartite entangled state, such as this beautiful state, the GHZ state. But this state, if you try to implement it with a photonic setup, you fall into a problem, which is that the way it's done currently is to generate a GHZ4. You generate two bell pairs, which is probabilistic. Each of them is probabilistic. And then you perform a fusion operation in the middle, which is basically a beam splitter, and which is also probabilistic. So probabilistic times probabilistic gives a low success rate of generating GHZ4. And if you want to go to GHZ6, you add even more probability and so on and so forth. So the more parties involved, the lower success probability you get. GHZ set creation has exponential cost with the number of parties involved. And this shows in any multipartite protocol that you want to look at. So this is one example that I call all-to-all entanglement. So the goal of this protocol is to generate entanglement between everyone. So I have like here a network of 6 parties, sorry. And I want to generate entanglement between everyone. So one idea is to just share a GHZ between everyone. And the other one is to share a bell pair between, so a singlet, however you want to call it, between every pair of parties. So here there is one source between every two parties. You can trust me. So basically, we are comparing one multipartite source versus 2 to the power n bipartite source. Obviously, there is much more hardware involved here, so you could imagine that it costs more. But the success probability of this is so low that actually, so these are the results. Actually, there is a trade-off. There is a number of parties after which it is better to use much more hardware, but with higher success probability, than to use the GLZ source. So you see, after above 6 parties here, it's better to use bipartite entanglement, which is the one in blue, over multipartite entanglement. And yeah, I have more results on multipartite stuff, but I don't have time to show it here, so I'm going to jump to the conclusions. So I've presented to you a method to estimate energy cost of quantum networking protocols. This is, I believe, the first time this has been done. We studied 2 figures of merit, the energy efficiency that will probably be the one used in future network, but that for now give trivial results. So we've looked at the cost of producing 1 gigabit of secret key, which gives you more concrete result of what happens now in the lab. We've identified critical components. So in DVQKD, the detectors are the main source of energy cost, while in CVQKD is the classical post-processing. And in multipartite networking is the generation of multipartite entangled state that is the critical part. Then there are other results that I didn't talk about. So we studied other multipartite protocol, conference key agreement protocol. So conference key agreement is QKD, but with many parties. One of us, experimentalists, actually went in the lab with a multimeter and looked at the energy consumption of each of the devices. It was interesting, but in the end, the value that it was giving was always lower than the one given by the datasheet, because the constructor gives you an upper bound of the energy consumption. So yeah, the result is just that the actual number is a bit less than what I showed you. And last but not least, we've implemented software that is available on GitHub with the full list of components that we've analyzed. And you can use it to estimate your own protocol or experiment. And yeah, we would be happy for people to use it, and most of us to add components to this so that we have the most complete library possible. So just a few outlook, and then I open the floor for questions. It would be, so this was supposed to be an outlook, but I went to the poster session, and the Gdansk people over there, Karol and Marek, already started to do a more fundamental study of the cost of distilling entanglement or generating entanglement in the network. So this will be out. I invite you to look at their poster. But discussing with them, another outlook that came out is also to make this calculation of secret key rate more precise. Right now, I didn't look at finite size effects and security parameters, so we will discuss more about this. I would like to apply this to photonic computing, so especially to Candela's, I don't know where it's to Candela's platform, because this straightforwardly applies to photonic computing. And yeah, find some epsilon security in QKD that then you could compare with classical protocols. And of course, the ultimate goal is to have the energy cost of a full-scale quantum internet with free space link, quantum memories, with complicated protocol, quantum repeaters, everything. So yeah, this eventually I will arrive there. And with that, I thank you for your attention.
Thank you, Raja. We certainly have questions.
It was too clear.
Thank you for this nice talk. Could you come back to the slide when you compare the GZ generation and yes, this one. I'm not sure about this 2 to N because it looks like I can locally generate GZ and then teleport by bipartite links to the other people.
Yeah,
so it looks like it's N.
Sorry?
So it looks like it doesn't take 2 to n bipartite connections to spread GHZ, or maybe I'm missing something.
So I'm not spreading GHZ, I'm spreading bipartite states.
Yes,
so
and
singlets.
I can, yeah.
So I have one bipartite source per pair.
Yes, and then you can have n such.
So,
Yes.
Everybody.
right. No, you're right. It's 2n. It's 2n. It's
This
not,
is n
it's not
squared
2 to
minus
it's 2n.
n.
It's 2 times n.
2 times n. Okay.
Yeah, yeah, sorry.
Okay, that's okay. Thanks.
I'm sorry. You're right. By the way, I can show you also the conference key agreement result. They are similar.
Okay. It's n square, I think. Okay. Okay. Somewhere at the beginning of the talk, you had this comparison where you showed that actually the cooling down of the detector is the vast majority of the energy needed. But then it's like basically just because you chose 1 gigabit of the code. So why 1 gigabit? Because like if you decide to produce 10 gigabits or 100, then the figures change. So why did you decide to take 1 gigabit?
We decided to take 1 gigabit because it was showing interesting trade-offs. So it's
but this, that's what I thought, but that's not really fair because, like according to my viewpoint, because if you really need to wait 24 hours to cool down, then you don't run your device for 20 seconds. No,
Exactly,
it's like
that's
that's not what you do. Then like you try to run your device for another day or something like that, and then the trade-offs might look
in the lab,
differently.
I could argue that now, when people perform experiment, that's kind of what they do. They turn on their device, they perform the experiment, and then they turn it off. So, yeah, I agree with you. Actually, here you can see the cost of generating 1 petabyte.
Okay, yeah.
So much more. And you find back the same thing as with the energy efficiency. No, I agree with you. I chose 1 gigabyte because it was starting to show some trade-offs.
Yeah, okay, yeah, that's why. But
it's like I can show interesting results.
yeah, but that's a tricky thing to tune the parameters to get the interesting results in some sense.
I mean, it is also, a result.